So in chemistry, we use significant figures to show how precise our measurements are. So we use rules to determine how many decimal places should be in the final answer of a calculation. Significant figures indicate how precise our measurement was to start with. So if we report a number that has too many significant figures, it looks like we were more precise than we actually were. If we report too few significant figures, it looks like we weren't very precise. So we want to give enough significant figures to be precise enough for what we're trying to do. So there are rules that determine how many significant figures are in a number, and then we're going to talk about how to know where to round off when we do a calculation. The way we determine how many significant figures we have is all non-zero numbers are always considered significant. So 1 through 9 will always be significant. For zeros, that's where it gets a little bit tricky. Whether or not zeros are considered significant depends on where they are in a number. So we're going to talk about 3 different types of zeros in a number and how we know whether or not they're significant. Before we get there, I do also want to mention really quickly here that sometimes we have exact numbers. So exact numbers are things like 12 eggs or 12 inches in a foot. We sometimes refer to these as counting numbers. So for example, 12 eggs, you could count that you have 12 eggs. Or if I have 6 chairs in front of me, I can count that there are 6 chairs. So if you can count how many there are of something, it's an exact number, and we consider that to have an infinite number of significant figures. So we don't have to worry about that when we're determining how many significant figures to give in an answer. For zeros, there's 3 different types of zeros. There's leading zeros, trailing zeros, and captive zeros. So leading zeros are those zeros that are at the front of a number when we have a decimal. Leading zeros are never considered significant. They're just placeholders to show us where the non-zero numbers actually start. So for example, 0.00392, these zeros here at the front are not significant because they're just placeholders. So only the 3, 9, and 2 are considered significant. So we have 3 significant figures in this number. For the next number here, we have a 0 before the decimal, and then we have 5 zeros. It doesn't matter how many zeros are there. If they're leading zeros, they're not significant. They're just placeholders for us. So we have 5 places between the decimal and the 4. Only the 4, 5, 6, and 3 are considered significant. So this number has 4 significant figures. For trailing zeros, sometimes they're significant and sometimes they're not. Trailing zeros are those numbers at the end of a number. If there's no decimal point in the number, like in the number 3700, zeros are not considered significant. So 3700 only has 2 significant figures. If there is a decimal point, then the trailing zeros are considered significant. So 140.00 would have 5 significant figures because the 1, 4, 0, and the 2 zeros after the decimal are all considered significant. Captive zeros are those zeros that are in the middle of a number. Those zeros are always considered significant. They're in between non-zero numbers, so they're trapped there. And the non-zero numbers around them are significant, so those captive zeros are also significant. So 16.07 would have 4 significant figures. 20.007 would have 5 significant figures. So leading zeros are never significant. captive zeros are always significant. So those are two cases where once we determine what type of zero we have, we immediately know whether or not it's significant. The only time there's a choice is when we have trailing zeros. So if there's a decimal, the trailing zeros will be significant. If there's not a zero, they won't be significant. So let's take a look at a few examples here. If we have the number 100 pounds, there's no decimal in this number, so those trailing zeros are not significant. So 100 pounds would only have one significant figure. 350.0 has a decimal, so those zeros are significant. So this number would have 4 significant figures. 0.0035, those are leading zeros, so those are never considered significant. So this number only has one significant figure. 10,000 is just like 100. There's no decimal, so there's only one significant figure. If we change that to 10,001, now we have captive zeros, so all of these numbers are significant. So there's 5 significant figures. So I'm going to let you try the last one on your own, and we'll get some more practice with this in class. We also need to look at, when we do calculations, how to round off. So when you're doing multiplication or division, the answer is limited by the least number of significant figures. So the rule is that you can only be as precise as your least precise measurement. So for example, in 278 has 3 significant figures. But if we look at our number of gallons, we have 11.70. There's a decimal, so that trailing zero is significant. So this has 4 significant figures. So we can only be as precise as our least precise measurement. So when we calculate 278 divided by 11.70, we get 23.7606, and this number goes on and on and on. But we're going to round to 3 significant figures. So the 6 would round the 7 up to an 8, which means that we would have 23.8 miles per gallon. Now when we add or subtract, we go by the number of decimal places. So we're limited by the number with the smallest number of decimal places. So if we add together 3.18 plus 0.01315, the 5 is considered significant. The 1 is, actually, we'll figure out what's significant once we add these together. So 5 plus nothing is 5, 1 plus nothing is 1, 3 plus nothing is 0, 8 plus 1 is 9, 1 plus 0 is 1, and 3 plus 0 is 3. So 3.18 only has 2 decimal places. Our other number has more decimal places, but we're limited by the one that has the least number of decimal places. So we would round this off to 3.19 for our final answer. So there's a few more examples here. So I'm going to give you a chance to work these out. So I want you to try these on your own. And then we're going to get some more practice with this, as I said, in class. So scientific notation is a way of writing really large or really small numbers without having to write all of the zeros in that really large or really small number. So for example, if we have a really small number like this one here, this tells us that we have some zeros here before we get to the 1. And if we didn't have this in scientific notation, we'd have to write out these 6 zeros. So to put a small number into scientific notation, we move the decimal to the right. So in this case, we go 1, 2, 3, 4, 5, 6, 7 places, and we keep going until we have one non-zero number before the decimal. Only one non-zero number. So then we're left with 1.2. Since we moved 7 places, we have a 7. And because this is a really small number and we moved our decimal to the right, the exponent is negative. If we have a very large number, we move our decimal to the left. So in this case, we go 1, 2, 3, 4, 5, 6, 7, 8, 9 places until we only have one non-zero number before the decimal. And since we went 9 places, and this was a large number, we moved our decimal to the left, the exponent is positive. So this comes in handy when we have things like, so what this number would indicate is that even if I move this decimal 2 places over, I still have 21 more zeros to go to write this number out fully. So this would be pretty inconvenient to have to write out this large number every time I used it. And you'll find out the significance of this number later on. But instead of writing out really large numbers like this, we use scientific notation. So let's get a little bit of practice here. Let's take the diameter of a sodium atom, which is all of these zeros with 372 after it. So we kind of group the zeros to make it a little bit easier to count them. And we're going to go to the right. So we're going to go 3, 6, 9, and then I'm going to go one more place over so that I have one non-zero number before the decimal. And I get 3.72 times 10 to the 9, 10. And since this was a small number, it's going to be negative 10. So 3.72 times 10 to the negative 10 meters. Now if we look at the second example here, the distance from the Earth to the Sun, if I go 3, 6, 9, and I still have a little ways to go, 10, 11, so I have 1.5 times 10 to the 11th meters. Now, we have to keep in mind significant figures when we do this. When I started this 150 with all these zeros here, this does not have a decimal anywhere in this number. So, I cannot make this 0 here significant, or any of these zeros. If I were going to count the significant figures here, there's no decimal shown, so this number only has 2 sig figs. Now when we count significant figures, when we're doing scientific notation, we only count the part at the beginning. this times 10 does not count for sig figs. So we're only counting the part at the beginning. 1.5 would be two significant figures. So don't add significant figures when you convert something to scientific notation. This number, these leading zeros are not significant. It had 3 sig figs to start with, and it had 3 sig figs in our final answer. So let's look at a couple of examples here where we take something out of scientific notation. So this one I have 9.9 times 10 to the 8th. This tells me this was a large number to start with because it's a positive exponent. So I need to take it out of scientific notation, which means I need to go the opposite direction that I would go if I were putting it in scientific notation. If I were putting it in scientific notation, I would go to the left. So I'm going to go to the right. So if I move that decimal over one place, I have 9, 9. And I still have 7 more places to go. So 1, 2, 3, 4, 5, 6, 7. And if I put the commas in here to make this number a little bit easier to read, I have 990 million bytes. Now the second example, I have a small number because it's a negative exponent. So if I were going to do a small number and put it into scientific notation, I would move my decimal to the right. So I'm going to go to the left to take it out of scientific notation. So I'm going to go one place over, and that gives me 0.5. Now in this case, I have a decimal here. So those trailing zeros are significant. This has 3 sig figs, which means that I have to keep the sig figs when I put this in scientific notation. Sorry, when I take it out of scientific notation. So this would be 0.500 grams. So we'll get some more practice with this in class. And in the next video, we'll talk about unit conversions and density.